Hi there folks, welcome to our videos on balancing redox reactions. Okay, we ended off last lesson with balancing the half reactions. We're now going to look at using those to balance full reactions. Okay, so as I said in the notes, we have a few steps that we're going to follow. Okay, so the first step is that we are going to separate the redox reaction into its two half reactions. So looking at this example here, we've got one half reaction where we're going to take this IO3 minus and we are going to the I2. The other half reaction that we're going to deal with here is the HSO3 minus transforming to the SO4 2 minus. Okay, so these are our two half reactions that we want to balance. Okay, so let's balance these two half reactions. Okay, first step that we need to do is we need to balance other atoms. Okay, so in this case here, first thing I've got is I got two iodines, so I need to put a 2 in front of this one. Okay, I then need to balance out our oxygens by adding water. I have 6 oxygens on this side, so I'm going to add 6 water to this side. After we've balanced our oxygens, we're now going to take a look at our hydrogens. I have 12 hydrogens on this side, so that means plus 12 H plus on this side. And then I can look at balancing my charge. We're completely neutral on this side, so all my charges on this side have to add to 0. I have 12 positive and 2 negative, so that means I need to then add 10 electrons, because that's the 10 negative, to add to these 2 negative to balance out that 12 positive. Okay, and so then a quick summary of this one is going to be 2 iodate plus 12 H plus 10 electrons is going to give us the I2 plus 6 water. Okay. Now if we were in basic situation, we would have to get rid of this 12 H pluses that we've added. However, we were told in the problem that this one is acidic. I will deal with the basic one in the next example. Okay. Well, now that we've balanced out this half reaction, we can look at balancing this half reaction. Okay. We've got one sulfur, so we're good there. We can then take a look at balancing our oxygens. Okay, I've got 3 oxygens here and 4 oxygens here, so I'm going to add 1 H2O. Okay. I'm then going to move to my hydrogens. I have 1 plus 2, so 3 hydrogens. So let's add that 3 H plus to this side. I then need to look at balancing out my electrons. Or my charge, sorry, using electrons. So I've got a -1 on this side, whereas on this side I have a 3 positive plus a 2 negative. Means I need to add in 2 electrons. Okay, so I've got a -2 plus a -2 gives me a -4. My 3 positives get a -1 on this side, balances out my -1 on this side. So, just giving ourselves a little summary on this side, we have an HSO3 minus plus H2O is going to give us with an SO4 2 minus plus 3 hydrogens plus 2 electrons. Okay, so we now have 2 balanced half reactions as we would have done in last week's lessons. Okay, our next step here is then to multiply each half reaction by an integer to balance out the electron transfer. Right, we've got to take this overall equation and balance it out. Okay, So what we're looking at here is I have 10 electrons in this half reaction, but I only have 2 electrons in this half reaction. We'll notice that we've got the electrons on the reactant side here and electrons on the product side here, so that is one quick double check to make sure we've done things properly. But I've got to balance out those electron transfers, so that means I'm going to take this entire equation and times it by 5. Okay? So when we write this one out, we can add these all up. Okay? So I'm going to take this equation here, I'm going to multiply it by the 5, and I'm going to add it to this equation here. Okay? So I have then 5 HSO3 minus plus 5 H2O is going to give me 5 SO4 2 minus plus 15 hydrogens plus 10 electrons. Okay. Now I can look at adding up this entire equation here. Okay. So we've balanced out our 2 half reactions. We've multiplied by an integer to balance out the electron transfer. Now we can add these 2 reactions together. So, is there anything we can cancel out? All right, well, first off, I had that 10 electrons and that 10 electrons. That's great. Let's get rid of those. We shouldn't have any extra electrons kicking around. I have 5 waters on this side. I have 6 waters on this side. So I'm going to cancel those out, and I'm going to be left with 1 water on that side. And then I had 12 hydrogens here. I have 15. So to cancel those out, that's going to leave me with 3 hydrogens. So when I write out my overall balanced reaction here, I have 2 iodates plus 5 HSO3 minus is going to give me some iodine, some I2, plus my 5 SO4 2 minus. I had 1 water and 3 H plus. Okay. So there we have our acidic condition balancing a redox reaction using 2 half reactions. So this was our initial problem that we dealt with. Okay, and in order to balance that all out, it would be really hard to bounce back and forth to try to balance this one out. However, the 2 half reactions weren't too bad, and then we end up with this for our final reaction. Okay, and these do tend to be a little bit more difficult and a little bit more messy than a lot of our other balancing reactions. Okay. Now it's a good idea to double check that we make sure we have everything we need on both sides. Okay. Well, I've got 2 iodines and 2 iodines. I have 5 sulfur. I have 5 sulfur. I have 5 hydrogens. I have 2 hydrogens plus 3 hydrogens gives me my 5 hydrogens. 6 oxygens plus 15 oxygens gives me 21 oxygens on this side. On my product side, I have 5 times 4 is 20, plus my 1, 21 on both sides. Okay, so our balancing works. Let's check out our next example. Okay, so as we get into our basic situation here, one thing we also want to understand is this idea of this disproportionation, okay? And so what's happening in this is we have one species that's going to undergo both oxidation and reduction, okay? And so if we just take a quick look here, okay? Now this ASO4, realize we haven't seen it, but it's going to be just this compound here, which has a 3 minus, okay? So if this is a 3 minus for this polyatomic ion, then that means that this iodine in this situation has a 3 plus for an oxidation number. Okay? And if we come over here, well, this I2, this is that elemental form, and we know that elemental form has an oxidation number of 0. Okay? So in that case, going from this 3 plus to this I2 0, that means that we've got a reduction happening. Okay? And then over here, our oxygens have -2 each, so 3 of those gives us a -6 on the oxygen. Our iodine and the oxygen have to add to a -1, so that gives this iodine a +5. Okay, so when the iodine goes from this compound to the iodate ion, we have a oxidation. Okay, so in this situation, our iodine is undergoing both reduction and oxidation, so that's that disproportionation reaction. Okay. And I mentioned in the previous set of notes when we were talking about these steps that when we want to balance these half reactions, we have our acidic situation, which we just dealt with, and now we're going to deal with a basic situation. So I'm combining both the disproportionation and the basic solution into one situation. All right, now that we understand what's going on with our two reactions, let's split these up into our two half reactions. So the one reaction that we're going to have is this ASO4 is going to break down into this ASO4 3 minus plus our I2. Okay. When we're dealing with this other reaction, we're going to have the same thing. This ASO4 is going to produce an ASO4 3 minus plus this IO3 minus. Okay, so those are the two half reactions we want to solve in this problem. When we're looking at this one here, we realize the arsenic and the oxygen are both balanced out. It's this, I've got one iodine, I have two iodines. So I need to put a 2 in front here, which means I also need to put a 2 in front of this one. Okay. As I mentioned, our oxygens are both balanced, so I don't need to add in any water, which means I'm not adding any H pluses. What I do need to do is I need to balance out my charges. And so on this side, I have 2 of these 3 minus, so I've got a -6 on this side, so I'm going to add in 6 electrons onto this side, and that will effectively balance out our charges. Combining this, we have 2 IASO4 plus 6 electrons is going to give us 2 ASO4 3 minus plus our I2. Okay, so we have that balanced half reaction. Let's take a look at this one over here. Okay. Again, we're going to start off with our other atoms besides oxygen and hydrogen. I have one iodine as a reactant, I have one iodine as a product, I have one arsenic as a reactant, one arsenic as a product. So that part is already balanced. What we need to take a look at though is now looking at balancing out those oxygens by adding water. Well, I've got 4 on my reactant side, however I've got 4 plus 3, 7 on my product side. So we'll add 3 H2O. Balance out our hydrogens. I now have 6 hydrogens here, so let's add 6 H plus onto this side. Now I can look at balancing out my overall charge by adding in electrons. I have a -3, or actually sorry, first off on this side, I have a 0 and 0, so I have a neutral on the reactant side. On my product, I have a -3 and a -1, so a -4. Plus these 6 positive give me a +2, so that means I need to add in 2 electrons to balance out to get that neutral charge. We can now sum up this side. Okay, so we've got that one IASO4 plus 3 waters gives us an ASO4, an iodate, IO3, 6 hydrogens, and 2 electrons. Now you may be saying, Mr. Finn, but you said that when basic we've got to add in hydroxides to balance out. We're going to do that after we recombine these. Okay? There's no point, because some of these we might have to have hydrogens in both of these half reactions, and we're adding hydroxides in both these reactions. Let's just save that until the very end. Okay? So the next step we have to deal with is we got to balance out our electron transfer. I have 6 electrons as a reactant in this half reaction, whereas I have 2 electrons in this half reaction as a product. In order to balance these out, I'm going to take this entire half reaction and multiply it by 3. Sorry, you can't see that on that side, so let's go 3 times this whole reaction. Now, my 6 electrons on my reactant will balance out with the 3 times 2, 6 reaction as a product on that side. Okay, let's take this whole piece now that we've multiplied it by an integer. We can then take that and add it to this half reaction over here. So we've got an additional 3 IASO4 plus 9 H2O. That's going to give us one more additional ASO4 3 minus. Oops, sorry, 3 of those because I forgot to do my multiply by 3. So we have 3 ASO4s plus 3 IO3 minus plus 18 H plus 6 electrons. I have 6 electrons on this side and 6 electrons on that side, so that effectively allows me to cancel those out. Okay, so let's cancel out those, and then let's just recombine everything and add these two together. I have 3 plus 2, so I have 5 IASO4 plus 9 H2O is going to give me 5 ASO4 3 minus plus 3 IO3 minus plus 1 I2 plus 18 H plus. Okay, so we broke this into our 2 half reactions. We balanced out those 2 half reactions. We multiplied by an integer so we can cancel out our electrons. And then I summed those 2 half reactions together into one overall reaction. Very similar to what we did in that first example. Now we can deal with this basic solution. Okay? And to deal with that basic solution, all we want to do is cancel out all of the hydrogens, or the H pluses, by adding in that same number of hydroxide ions. But we need to make sure that we are doing that to both sides. Okay? And so what we get here is these 18 hydrogens plus these 18 hydroxides gives us 18 water. Well, I had 9 waters as a reactant and I've got 18 waters as a product, so I can cancel those out and rewrite this out as our overall reaction. So, what do we get? We have our 5 IASO4 plus 18 hydroxides. Now remember, these 9 waters are canceling out with 9 of those. Okay, so I no longer have any waters on my reactant side. On my product side, I get my 5 ASO4 3 minus plus 3 IO3 minus plus my I2, and then my 9 waters cancel out part of these 18 to leave me with 9 waters as a product. Okay, so that is our method of solving these solving these balancing redox reactions using half reactions. We've seen an acidic case, and we've now seen a basic disproportionality situation as well. Okay, let's move on to our next method of solving these reactions, which is balancing the oxidation number. Okay, so our second method of balancing out these redox reactions is using this method, using oxidation numbers. Specifically though, what we're looking at is this delta ON, right? Okay, this change in oxidation number. You might not be able to see that, so let's write that in blue here. Okay, so delta ON, our change in oxidation number. Okay, so in this method, first thing we gotta do is we gotta figure out what all of our oxidation numbers are. All right, start with our MnO4 minus. Okay, I have 4 oxygens, which is a -8. If my entire thing has to add up to a -1, that means I have a +7 charge on my manganese. Looking at my nitrogen dioxide, okay, overall, this has a net charge of 0. Okay, we have a neutral compound here. So if I look at my 2 oxygens, it gives me a -2. That means that my nitrogen here must be a +4. All right, we've got a total of -4 from our oxygen, so we must have a +4 on our nitrogen. Okay, when we take a look at our NO3, okay, now we're dealing with that polyatomic ion with a -1 charge. I have 3 times -2 on my oxygen, so I have a -6 on my oxygen. This whole compound adds to a -1, so that must mean I have a +5 for my nitrogen. And then when I'm looking at my metal over here, I just look at the charge that's on that metal, so I have that 2+. Okay? And so what we're seeing here is we have our nitrogen going from a +4 to a +5, so our nitrogen is being oxidized. Our manganese is going from a +7 to a +2, so it is being reduced. Okay, so when we go to look at this, we want to look at what's this, this delta ON. Okay, so we've got this situation here, okay, where we have a delta oxidation number of equal to +1. Okay, it's the change in oxidation number. We go up by 1. Whereas when we're looking at this species here, this manganese, going in this direction here, our delta ON is going from a +7 to a +2, so that's a -5. Okay, our oxidation numbers overall need to remain the same, because remember that change in oxidation number is just the transfer of electrons. And as we saw in those previous examples, we need to balance out that change or that transfer of electrons. So looking at this delta ON, this change in oxidation number of +1 compared to this change of -5, I must have to multiply this whole thing by a value of 5. Okay, and then my manganese is going to just be multiplied by 1, right? We want to have that same value. So let's just rewrite this out. I have my MnO4 minus plus 5 NO2 gives me 5 NO3 minus plus my Mn2 plus. Okay, now we're just going to treat this like our regular reaction, and we're going to start off with those steps. Other atoms. Well, I've got 1 manganese and 1 manganese. I've got 5 nitrogens and 5 nitrogens, so that part's okay. I then want to take a look at my oxygens. Well, let's see, what do we have? I'm just going to write this off to the side. Oxygen. We've got our reactant and we have our product side. let's see, I've got 4, and 5 times 2 gives me 10, so I've got 14 on the reactant side. 5 times 3 gives me 15 on my product side, so I need to add in 1 H2O. Okay. I then want to balance out my hydrogens. I didn't have any of my species and other species outside of this water, so this one's pretty straightforward. I have 2 in my reactant side, so I'm just going to add in 2 H plus on this side. I'm just doing this chart as a way to help make sure that everything is in the right order and that we're following all these steps so we can easier count these. Okay. You can also use this method to help double check, because once you balance out your redox reactions, everything on both sides should be the same. Okay. So this double check allows you to make sure that you've added everything up properly as you've gone through this. The last thing we want to do is we want to take a look at balancing out the charges. Okay, so I can take a look at this side here. I've got a -1, 0, and 0. So I have a charge of -1 on this side. If I look over here, I've got 2H plus and an Mn2 plus. So I've got a 4 plus and I've got a 5 times a -1. So I've got a -5 and a 4 plus gives me a -1 charge on this side. I had a -1 charge on this side. So I don't need to add any electrons, which should be the case, right? If we did this part correct, all electrons should already have been taken care of. So now we just need to rewrite this out as our overall reaction, as neat as we can. And so we have our MnO4 minus plus 5NO2 plus our 1 water is going to give us 5NO3 minus plus our Mn2 plus 2 H pluses. We're in acidic conditions, so we're allowed to leave this H plus, and we are now done balancing out this equation. Let's take a look at a basic disproportionation equation for our second example. All right, so here we are with our basic disproportionation reaction again. And I guess I should make one comment here. Although both these examples I've done today are using basic and disproportionation in the same sense, that doesn't mean that's always going to be the case. Okay, you can have an acidic disproportionation reaction, or you can have just a regular basic. Okay, but rather than doing 3 different examples, one for acidic, one for basic, one for disproportionation, I'm just trying to combine those last 2 into one example to try and limit the number of examples we're doing and try to keep this video to under an hour. Okay, and we will do that. So don't worry, there's not another half hour left. Okay, we will not take that long. All right, but as we're taking a look at this one, for this first step, when we have this disproportionation, we need to write this out so that we want to see the oxidation and the reduction happening at the same time. So we're just going to adjust this and say we have a P4 plus a P4 is going to give us this HPO42 minus plus our PH3. Okay. This is just helping us to balance things out. And we'll see how things end at the end. We may be able to get rid of one of these at the end. But first, let's just start by looking at what are our oxidation numbers. Okay. P4, as I mentioned when we were dealing with these, the rules on assigning oxidation numbers, these are the elemental form of phosphorus. So that means that both of these have a charge of 0, or an oxidation number of 0. Okay. We can then look at this one here. Okay. Remembering that hydrogens are a +1 unless they are a metal hydride. And our oxygens are a -2. So 4 times -2 gives me a -8. This entire polyatomic ion has to have a -2 charge. I currently have a -7. So to balance out this -2 means my phosphorus must have a +5 charge in this species. And when I look at this one here, remembering again that my hydrogens have that +1 unless they're with a metal. So in this case, they are a +1, so that's a +3 for my hydrogen. This whole compound is neutral, so that means my phosphorus must be a -3. All right, so when we're going from the P4 to the HPO4, we are going from a 0 to a +3. Okay, so this one is being oxidized with a delta ON equal to 5, +5. Okay. We then look at our other situation where we've got this P4 that is a 0 charge, or 0 oxidation, going to this -3 oxidation number, so we have a delta ON equal to -3. That is the reduction portion of this example. All right, so now that we have our change in oxidation numbers for both our oxidation and our reduction, we need to multiply these to get a common value. Okay, so a lot of times the easiest way to do is to multiply this one by the value of this one and multiply this one by the value of the top. Or essentially just looking for that common value, the lowest common multiple. In this case, we're looking at +15 and -15 to cancel those two out. So I want to rewrite this out then as an overall. So I'm looking at this outside one. So I've got 5 P4. Looking at this one inside here, I had 3 P4. Over here, this is part of this initial one where I've got times by 3, so I've got 3 HPO4 2 minus, and then this bottom one, or this far one here, is going to be +5 pH3. Okay. Now, we want to pay attention to our numbers here, and so other atoms, right? We deal with those first. I've got 5 times 4 and +3 times 4, so I have 8 times 4. I've got 32 phosphorus on this side. Okay. However, on this side, I've only got 3, and over here, I've got 5. So essentially, we went from this P4 to this single P, we went from this P4 to this single P. So that just kind of helps us understand that I've got to take this, multiply this by 4 to give me 20, and I have to multiply this one by 4 to give me 12. And then, like I said, we had 8 times 4 on this side. I've got 12 plus 20, so 32 and 32 phosphorus. That part now balances. Okay. I then need to look at my water. Or sorry, my oxygen by adding water. And in this situation, it's definitely going to be helpful to realize that I've got 0 on this side for both hydrogen and oxygen, and I've got to try and balance out on this side. Well, luckily I've only got the one situation where I've got water here, so 12 times 4 oxygens means I have to add in 48 H2O. Okay, 48 water. I can then take a look at my hydrogens. I've got 96 on this side. So let's just look at this. Hydrogen, 96 on my reactant side. And I gotta look at my product side. Okay. Well, I've got 12 here. Right, 12 times 1 plus 20 times 3. So I've got 60 plus 12 means on my product side I have 72. Means I need to add in 24 H plus on that side there. Okay. Before I go to add this all up and balance it out, We can look back and see that we have our basic situation, okay? Which means I've got to get rid of all of these 24H plus. I'm going to do that by adding in 24 OH minus, and to avoid any problems, I'm going to add in 24 OH minus on this side. That means these here create 24 H2O to cancel out half of the H2O on this side. Okay, let's run out of space on the board here. So I'm going to get rid of this middle section where we looked at that oxidation number change. And let's just rewrite this. So what do I have? I've got 8 P4. I had 24 waters on this, I had 48 on this side, so I'm going to have 24 H2O on my reactants, plus my 24 OH minus, and then on this side I have, going to my product side, I have 12 HPO4 2 minus, plus 20 PH3. Now, before I look to double check everything works out here, I just want to look at these coefficients. 8, 24, 24, 12, 20. All of those are multiples of 4. So let's divide all of those by 4. And we would be left then with 2 P4 plus 6 H2O plus 6 OH minus is going to give us 3 HPO42 minus plus 5 PH3. Okay. Those simplified numbers will just make it a little bit easier to do our double check to make sure everything balanced out. Okay. So one thing we can check out is our charge. I've got 6 negative and I've got 6 negative. Okay, so charges work out. 8 phosphorus. I have 3 plus 5 is 8 phosphorus on that side. 6 oxygen plus 6 oxygen is 12 oxygen on my reactants. And I've got 12 oxygens over here in my products. I have 12 plus 6, 18 hydrogens as reactants. I have 5 times 3 is 15, plus 3 is 18 hydrogens. Everything balances out on both sides. Okay. Now you may find that one of these methods is going to be easier than the other. That's okay. I'm not going to ask you specifically to solve it using the oxidation number or the half reaction method. However, I will ask you to balance out half reactions. I will ask you to balance out overall reactions. When it comes to those overall reactions, it's up to you to choose. Dealing with those half reactions, follow those steps, assign our oxidation numbers, should be good to go. All right. One last example we're going to do today is we're going to talk about titrations, or specifically redox titrations. All right, so we've dealt with these titrations several times. Okay, we talked about them in solubility, we've talked about them in acid bases, and we can also use those in redox reactions. Now, the one key to all of these titrations is some sort of a color change. Okay, when we're doing that solubility, we're usually using a white precipitate that's going to turn into a yellow or a red precipitate. When we're talking acids and bases, we got some sort of an indicator, usually like phenolphthalein, which goes from clear to a bright pink to let us know when those endpoints are. Now, when we're dealing with this redox titrations, we're usually using this KMnO4, okay? This MnO4 plus ion, sorry, MnO4 minus ion, has a very dark, rich purple color. In acidic conditions, this will turn clear once it's fully transformed into the Mn2 plus, okay? And we use this to help understand when that endpoint is. When we no longer see that purple color, the moment it's gone, we've reached that endpoint, and that allows us to see, calculate that unknown concentration. So the problem I pose today is determine the concentration of this FeSO4 by using the 0.0200 molar KMnO4. 25 mils of the iron sulfate needs 27.4 of the potassium manganate, or permanganate. Okay. Now I'm going to give you, a lot of times we'll give you the basic reaction you'll have to balance out, or sometimes we'll even give you the full reaction already balanced out, and you just got to do the calculations. I'm going to do both steps. Okay? So the first one we want to do is we want to realize that in this situation, and it'll be given to you, don't worry, the sulfate is a spectator ion, and so is the potassium. Okay? They are just going to be dissolved. So what we're looking at here for our reaction is we've got this MnO4 minus plus Fe2 plus, right? We know it's the 2 plus version because it's the sulfate ion is a 2 minus charge, so that means the Fe is the 2 plus. And then from here, we are going to get the Fe3 plus plus manganese 2 plus. Okay? So I'm going to solve this using our 2-half reaction method. So I have MnO4 minus is going to be Mn2 plus, and I have my Fe2 plus is going to the Fe3 plus. This reaction is nice and easy. In fact, it's on our data table at the back of the textbook. And so to go from a 2 plus charge to a 3 plus charge being oxidized here, we have to add in an electron being released. Okay, on this side, well, we got a 1-to-1 on those manganese. I've got 4 oxygens, so let's add in 4 waters. I now have 8 hydrogens, so let's add in 8 hydrogens. This side here is a +2 charge. Over on this side, I had a +8 and a -1. Gives me a +7. So to go from a +7 to a +2, I need to add in 5 negative electrons to balance this out. Overall reaction here, MnO4 minus plus 8 H plus 5 electrons is going to give me my manganese 2 plus and 4 water. Remember back to those examples we did earlier, once I've balanced out my 2-half reactions, I've got to balance out those electrons. 5 electrons as reactants from this reaction. I've got 1 on this side, so I'm going to take this whole reaction times 5. I can then add that in, and I have 5 Fe2 plus is going to 5 Fe3 plus 5 electrons. Same number of electrons on both sides, cancel each other out. My overall reaction for this equation, MnO4 minus plus 5 Fe2 plus 8 H plus gives me an Mn2 plus 5 Fe3 plus 4 water. Now, as I mentioned earlier, in order to go from the purple MnO4 minus to the clear Mn2 plus, it's an acidic condition, so I can leave this 8H plus here, and I now have this balanced equation to help me solve my overall concentration of the unknown solution. Okay. I'm just going to get rid of this here to have a little bit more space, and we have that down here anyways. Okay, so what are we looking at here? We have 27.40 milliliters of my MnO4 minus. And that MnO4 minus had a concentration of 0.0200 molar, which could be moles per liter, but we also know that that's millimoles per milliliter, and this is at MnO4. Okay, so the milliliters MnO4 cancels milliliters of MnO4, and so when I multiply this out, so when I multiply this one all out, I end up with 0.548. Okay, so that is 0.548 millimoles of my MnO4 minus. But I wanted to know what was my concentration of the Fe plus. So to convert my MnO4, I need my molar ratio from down here. 5 Fe2 plus for every 1 MnO4. So times 5 Fe2 plus for every 1 MnO4 minus. Okay. That gives me 2.74 millimoles of Fe2 plus. And that came from 25 milliliters of iron. So 2.74 millimoles divided by 25.0 milliliters. Okay. This gives me a concentration of 0.110 millimoles per milliliter. And I just want to remember that. Millimole per milliliter is the same as mole per liter, is the same as our concentration molarity. So we end up with 0.110 molar FeSO4. Okay, and so that is how we do our titration calculations. Okay, hopefully that helps. If you have any questions, please make sure you post those. I'll get around to them as soon as I can. Otherwise, be safe, stay healthy.